Okay, hey everyone. So today I'm going to be talking about radiation survey meters. So most of the time you'll come across gas-filled survey meters. So essentially similar construction to ion chambers. So you have anode and cathode. Basically the entrance window down here, which will allow both alpha and beta radiation through. Gamma radiation can come in through the sidewall. It's generally a thick wall, so that's why alpha and beta radiation can't get through, because you generally have either high or low pressure in your GM tube, in your survey meter. So it's sealed, filled with a noble gas, either argon or helium are the most likely, and both GM and proportional counters have quench gas, which help with stopping avalanches. So when the ionization they have such a high voltage that one ionization causes multiple ionizations, and that creates an avalanche, and the quench gas just helps stopping that. So you have an outer cathode wall and a central anode, and the anode is always positive in these survey meters. Gas-filled survey meters again. So this is your plot of voltage versus your signal. As you increase the voltage, you're in this first region. So at the start you're in the recombination region. So here, basically not collecting all the charge you're measuring. So Tom sort of hinted at that before. So at low voltage, there's lots of recombination and you're not collecting all the signal. Then you start to plateau at this ion chamber region. So this is where you measure your dose. So this is where these chambers operate at that Tom was talking about, and this is where the charge collected is proportional to your dose through calibration factors. Then as you increase the voltage further, each ionization will cause what's called an avalanche effect. So each ionization the voltage is so high they accelerate across the potential and they create successive ionizations. So it basically creates an avalanche, and you're actually getting more signal than just what the radiation produces. So you're getting more signal, more. In this region, it's called the proportional region because the signal you get is proportional to the energy and type of radiation. So for example, this might be alpha radiation, which has a high signal, and this is beta radiation, which has a low signal. This region here is basically useless, so limited proportionality. Then you have your Geiger-Müller region. So in this region, it's very high amplification factor, and your signal you measure, so each pulse, the signal is independent of the type of radiation. So any radiation that hits the tube will give the same signal regardless of what it is. Then as you go higher voltage, you get what's called the region of continuous discharge. So your voltage is so high that it's just causing ionizations even if there's no radiation present. And these are just approximate values for where these regions are. So the actual values for these voltages will depend on the ion chamber construction. So it depends on the pressure, the size, and the type of gas you're using, which will dictate what these voltages are. So types of survey meters. As I mentioned, the ion chamber survey meter. So this operates in the ion chamber region, which is here. So this is the ion chamber survey meter. So this is the fluke survey meter. Just put that there. So they can operate in pulse mode, but they normally operate in current mode. So you measure the currents produced by the radiation. It's the least sensitive survey meter, and that's why they generally have very high pressure gas, because the higher the pressure of the gas, the more sensitive they are. And it's used to quantify the radiation exposure. So use it during shielding surveys to quantify the dose to various points around your shielding. Proportional counters, so they operate in pulse mode in the proportional region of the ion chamber graph. So the amplitude of the pulse you get for each ionization event depends on the type and energy of radiation. So you can use this to determine the type of radiation. So you can determine the energy of the radiation and if it's an alpha or beta radiation. So for example, where we would use that is for contamination. So if you don't know what the radioisotope is, you can use this to determine what it is. And then Geiger-Müller counters operate in the Geiger-Müller region in pulse mode. They're the most sensitive survey meter because a small ionization event can cause a large signal. Then the amplitude of the pulse is independent of the radiation source. So you're basically just measuring the number of pulses. And it's basically used as a portable instrument to indicate the presence of radiation. So you're not quantifying what the radiation is or how much there is. It just says there's radiation here. And so this one is an example. We've also got another one here. So this is the Automess servometer. We use this in brachytherapy. So we're not allowed to enter the brachytherapy bunker without this on hand, just to say the source isn't eligible or not producing radiation. It basically tells you. And it beeps, so basically the higher the radiation, the louder it gets, basically. If I can have it around to show people. Okay. And then of course, certain filters can be added to the end of it to discriminate radiation. So you can remove alpha and beta radiation and only measure gamma, or you can take the filters off to measure alpha and beta. So neutron detection, I'm not going to pass this around because this one's heavy. So neutrons have a very low cross section for interaction, so they basically they're a bit like photons, they just go through anything. And certain materials have a higher cross section. So boron, hydrogen, and helium, they have a much higher cross section of interaction than any other material. So the most common type of neutron servometer is a VF3 gas field detector. You can also get helium gas field detectors, but the boron interacts with the incoming neutron to produce lithium and an alpha particle, and then this can detect the alpha particle. The cross section reduces with the speed of the neutron. So the faster the neutron is, the less likely it is to interact, and so we need to slow them down with a few centimeters of hydrogen. But the hydrogen dense material. So this will slow down your neutrons, but it will reduce your detection efficiency. So you'll actually detect less signal with hydrogenous material. So it's basically a compromise between being able to detect the neutron and getting absorbed by the material completely. And we use a proportional counter because basically we can say, all right, this is our energy peak for this reaction. This reaction, the bottom one, and this is our energy peak for this reaction. So this is basically the size of our signal we get. And this here is the size of our signal, the pulse we get for low amplitude gamma radiation and electronic noise. So what we say is we're going to put a threshold, say here, and completely ignore anything less than that threshold. So we're only picking up neutron radiation. So this is a great advantage of proportional counters. We can just completely ignore other signals and say, okay, this is my signal I want. Yeah, and it's very heavy as well, so yeah, you don't really want to be holding for too long. Energy responsive servometers. So servometers have, at low energy, they have lowest response, and they're generally calibrated at a certain energy. So this is the energy response of this servometer that we passed around, so the fluke servometer. And you want to essentially operate it at so the servometer depends on, so different servometers have different sensitivities to the energy. So you want to operate it at where it's supposed to be. So this one, for example, you're supposed to hold it like this because the most sensitive direction is at the face of the servometer. So that's how you want to operate it, yeah. And you want to point that towards your radiation. The angular response. So again, this servometer, again, it has very low response to low energy photons at the back, but it has a higher response to the side and even higher at the front. And then, for example, like a cesium source, there's not really much angular dependence, but you should always face it towards your radiation, and preferably at arm's length, just you don't really want to walk up towards the radiation source. And then you should always operate according to the manual. QA of servometers. So servometers should be calibrated at an interval not exceeding 3 years. So this is this safety report series 16 tells you how it's calibrated, and it's sent off to a primary standards lab like an ion chamber. Panzer recommends doing a constancy check with a check source at least every 12 months. And for example, a cesium check source, because cesium has a very long half-life of 30 years, so you can keep it around and correct for the decay and basically just check that your servo meter is still responding correctly. If it's not responding, it could mean that there's a change in your servo meter sensitivity, or you've damaged it somehow. And then this table here, I couldn't really find much about QA, but this table is recommended in nuclear medicine departments. So you do a battery check, a contamination check, which is basically a background reading every day, and they also recommend doing a constancy check for your servo meter every day. We don't do that here, we just do it, but we do a battery check and contamination check before we use it, and then calibration they recommend annually, but we only do it 3 years here. So shielding survey, so this is an example where you use basically all these types of detectors. So when you calculate your shielding, you basically set a dose constraint. So a dose limit is a legal requirement for your shielding. So legal requirement of dose to radiation workers of 20 millisieverts per year and public of 1 millisieverts per year. But dose constraint is what you set to optimize your shielding. So NCRP recommend 5 millisieverts a year for radiation workers and 1 millisievert a year for the members of the public. So they recommend you, when you do your shielding calculations, you do this. I'm not going to talk about how to do shielding calculations, I'm just going to talk about how to use survey meters to determine the adequacy of your shielding. So when you do a shielding survey, the equipment you need Geiger Muller counter to find hotspots, because it's a lot easier to find hotspots with GM tube because they're much more sensitive. Ion chamber servo meter to measure the instantaneous dose rate at these hotspots. So GM tube can't quantify the radiation, it can just tell you that it's there, and then the servo meter you use to basically measure the amount of radiation that's there. Neutron servo meter is required if the energy of your beam is higher than 10 MV. If it's less than 10 MV, you don't need a neutron servo meter. The reason is because the threshold energy for photonuclear reactions is roughly about 10 MV for most materials, so neutrons will start being produced above that energy. And you also need a scattering material to simulate a patient for patient scatter radiation measurements. And all servo meters should have a calibration certificate traceable to a primary standards, and they normally come with an uncertainty estimate as well. Okay, so this is a design of a bunker we have here. So primary barriers, secondary barriers around here, and this is the maze. And then this is where the staff are, and this is the what's that called? Where all the machinery is. Yeah. And then there's an adjacent bunker here and adjacent maze here. So where do you want to survey your points? So you basically survey at all the points you did your calculations at when you calculated your, before you installed your bunker, you calculated the required thickness of the bunker, and then you at certain points. So there are two types of areas. So you have uncontrolled areas, which are where anyone can be essentially. So any member of the public can basically walk around in those uncontrolled areas. So that's where you set your dose limits to be 1 millisievert per year. And your controlled areas. So this is where only staff or patients being treated are essentially up. So that you get adjacent bunker, the maze, and your control room. So there's very limited access in these areas. Then you basically define your points. So you have your primary shielding points here, and you've got your secondary shielding points here. So this is where, so the primary beam will come through this way, so your Linux here, and when the Linux facing this way, it will go directly through the wall here, and when it's going this way, it will go directly through the wall here. And then scattered radiation will basically bounce off the patient or bounce off the Linux head and just go out all over the place. And you've also got scatter through the maze as well you have to consider. Okay, so primary barrier measurement, you set maximum field size, collimator 45, and the beam directed straight at the primary barrier, and then you stand here and do your measurement. So you stand here, use your Geiger counter to measure the hotspots, and you also do it here as well when the beam's directed this way. And then you use your servometer to quantify that hotspot. Then this is the equation used. So it's your instantaneous dose rate you measure times, the time average dose rate in a week. So the measured dose you would receive in any 1 week is your instantaneous dose rate times your workload, which your workload is estimated when you first install the linac. So it's basically how much dose do you expect to be delivered to the isosensor in any 1 year, in any 1 week. And it's based on your number of patient workloads and the types of treatments. Then your use factor is basically how much of the time will the beam will actually be directed at the wall. So will it be, and generally for VMAT treatments it's roughly a quarter of the time. So if you assume that, if you basically divide every arc into 4 quadrants, it's basically at that wall for about a quarter of the time. And then this is just your reference dose considered. So it's basically your reference dose rate. Then your actual dose delivered to any person in that area will be your time average dose rate times your occupancy factor. So T is basically, so this is it's basically a driveway here. So you basically estimate what percentage of the week will someone ever be standing here. And for this sort of, and NCRP 151 actually state what occupancy factors are. But this T, this W, and this U, and the D naught, that's all basically calculated when you're doing your shielding calculations, and you're basically just using this survey to compare to your shielding calculations. So then head leakage. So this is basically, you have jaws fully closed, gantry at 0 degrees, and basically it's the contribution of scatter from the head. So basically radiation beam scattering off all the different components in the linac head, such as the flattening filter, jaws, target. So basically these are all your secondary barrier points. So you want to measure this dose at all these points. So basically it's just scatter. Measure your instantaneous dose rate leakage. Yes. Then your patient scatter measurement. You basically want to simulate a patient treatment. So you have a phantom here that's roughly the size of a patient, so 30 centimeters by 30 centimeters by 30 centimeters. You basically direct the beam straight at it, and you basically measure the dose delivered at these points using your servometer again. And again, you use Neutron servometers and ion chamber servometers to quantify the dose delivered here. Then you basically do a similar calculation to calculate your weekly dose rate, and then compare that to your measurement, and there should be a T there. I forgot that. The equation's a bit wrong there. But yeah, so you compare that to your shielding calculations to basically determine if your calculations were correct and determine the adequacy of the shielding. And then other considerations, so sky shine radiation, so it could bounce off the atmosphere or the roof and come down to a person standing out here. So you want to basically account for that and do surveys, and do a survey sort of out in the distance. And ground shine, so for example, so if you have less shielding in this component compared to here, so this door is lead plus polyethylene, and then this is just a concrete floor, so that basically there's more dose that could easily bounce off and come through here. So you, in most designs they might have added shielding here, but you should measure that just in case they don't. And then also door maze is another thing you should measure. You'll get more neutrons coming through the door or maze than you would coming through the concrete barrier, because concrete is very good at absorbing neutrons. Environmental servometers. So these measure the exposure at a point over a very long period of time, so generally 3 months. And it's normally performed after you've installed and you've already done your survey. So you do your preliminary survey, you calculate your dose, but then you want to actually measure what the dose is when you're using it clinically. So you place, they're normally either TLDs or film, and you just place them around in your points, stick them on the wall, and you just leave them there for 3 months while the machine is being used clinically, and then you actually measure your dose. So this basically you make estimations for your workload and your use factor, but this actually measures the real dose that's been delivered there in the certain period. And TLD or film are used because they don't require cables, they don't require batteries. You can leave them there for 3 months without worrying about them. And so TLD 100 is a type of TLD that's actually very stable over a 3-month period, so they don't lose signal as much as, and of course you want to protect them from environmental conditions, so placing plastic envelopes just in case it rains or things like that. And preferably if they're outside, you want to keep it out of the sun as much as possible because they can be affected by UV. And then personal dosimeters, so they basically measure the effective dose of the whole body, or you can also get ring dosimeters that measure dose in the hands. So TLDs, OSLDs, and film are often used for 3 monthly badges. So you have a 3 monthly badge, so this is a TLD badge, and it gets replaced every 3 months, and they measure the dose of it. Various filters can be used to discriminate different types of radiation. So you can have, so this one is, I believe it's just got one measurement, but you can get TLD badges that have 4 different points of this film badge here, and it's got various different filtration material to basically remove alpha, beta, or neutrons. And then electric dosimeters, so this is an electric dosimeter here, the battery's been taken out. So this is, you'll just use it basically in more high-risk situations, so this will give you immediate readout of dose that you've been exposed to. And we only use them in brachytherapy, so just in case there's an emergency. So we don't expect the staff to be exposed to too much radiation, but in case there is an emergency and that staff has to go into the room while the source is out, we want them to have an electronic dosimeter so we can basically say what dose they would get given straight away. Yeah, thank you. That's all I have.